In today's lesson, we're going to be talking about the sine law. So previously we were spending some time taking a look at solving for lengths and angles of right angle triangles. Again, if you missed those lessons, I'll link that in the top right hand corner. Now we want to take a look at what do you do if you have a triangle that is not a right angle. What are some techniques that we have? The first technique we have to work with is the sine law. First thing to note is that how do you label a triangle? Capital letters usually indicate the angle that you're referring to. So this would be angle A, this would be angle B, and then this would be angle C. And typically the opposite side is labeled with lowercase a, opposite side of angle C is going to be labeled with lowercase c, and opposite side of angle B will be labeled with lowercase b. In this case here, C represents the length of this leg of the triangle, B represents the length of this leg of the triangle, and lowercase a represents the length of this leg of the triangle. So what does the sine law state? Well, the sine law states that the sine of A, angle A, divided by the length of A, that ratio must equal the sine of B divided by the length of B, which also must equal the sine of angle C divided by the length of line segment C. So in this situation here, we've got a relationship between the length of the triangle and an angle in that triangle. Now, alternatively, you could also express this with the length on top. So in this case here, you can have A over sine of angle A equals the length of B divided by the sine of angle B equals the length of C divided by the sine of angle C. And you can, depending on what problem you're using, you can choose which relationship you want to use. Typically what the strategy is if you're looking for angles, you're going to use this side of the sine law. Whereas if you're looking for lengths, you're going to want to keep that length in the top, in the numerator, and in which case you'd be solving for these ones. Okay, let's take a look at some problems. All right, so for this first problem here, notice here, I don't have a right angle in this triangle, and because that, I can't use sine theta or cos theta. So how can I do this here? Now, first off, notice they want me to solve for length x here. So depending on the question you're going to get, it's going to be labeled in all different letters. If you're used to using the sine law with A, B's, and C's, what we should do is label this triangle with A, B's, and C's. So in this case here, I'm going to go capital A, capital B, capital C. Notice I labeled my triangle going in the clockwise direction. Now directly across from angle B is lowercase b, directly across from angle C is lowercase c, and lastly, directly across from angle A, we're going to write that as lowercase a. So instead of solving for x here, we're just going to solve for A. All right, so that we can match our sine law formula. So now if I want to solve this question here, I'm going to use the sine law with the length on the top. So in this case here, it's going to be A over sine of angle A, which in this case is 50, equals, so A over sine of A equals, well, what ratio? I can choose B over sine of B, like I can find what sine of B is, because I can find angle B, right, because it has to add up to 180, but I don't know the length of the line segment B here. So instead of doing that, I'm going to go C over sine of C. So we're going to use these two instead, because I have these two values. So in this case here, this becomes C, which is 54, over the sine of 34. Now notice here, I have an equation, and I want to solve for the variable A. So the sine of 50 is just a number. Right, that sine of 50 that we have down here, this is just a number. So if this was a 2, we would multiply across by 2. If this was a 3, you multiply across by 3. It's a sine of 50. I'm just going to multiply across by the sine of 50. So by doing that, we've now isolated the A, and we're now computing 54 sine 50 divided by the sine of 34. If you calculate this, you get approximately 73.98 units. Okay, so the length of line segment A here is approximately 73.98 units. Now just a quick observation as you go through these problems, you can kind of see whether things are making sense. Notice we've discussed this before. A larger angle means larger opposite side. So if they're telling me that for 34 degrees the opposite length is 54 units, the answer I get must be larger than 54. And in this case here, I had an angle of 50 degrees, and I got a measure of 73.98 units, which was obviously larger than your 54. So you can kind of use that to keep in check to see whether you're on the right track. Again, It doesn't mean that the answer is correct and you didn't make any mistakes, but you can catch some errors as you go through these problems. Okay, let's try another. So for this triangle here, now instead of solving for the lengths of sides, we want to solve for the angle. So I want to solve for angle theta here. So let's take a look. I'm going to first label my triangle. So we're going to go A, B, C. Across from angle A is length A. Across from angle B, length B. Across from angle C, length C. And now in this case here, I want angle A, and I have this length here. So we're going to use these two values. So now I'm looking for the angle this time. So I'm going to go sine of A over 106 equals. Now I have to do sine of, I can either do sine of C or sine of B. I actually don't have angle B. So I'm going to have to go ahead and find angle C first. So it's going to be sine of 47 degrees over 78. Now I want to go ahead and solve for A, but before I solve for A, I have to solve for sine of A. So we're going to multiply across by 106. Now at this point here, I would get this to approximate value. I would round to 4 decimal places. So if I round this to 4 decimal places, I get approximately 0.9939. Now we go ahead and take the sine inverse of both sides. And the sine inverse of 0.9939 gives me an approximate value for angle A of 83.66. So therefore angle A is approximately 83.66 degrees. Okay, so for this problem here, we have two tracking stations are 20 kilometers apart, and they're tracking a rocket in the air. You know that from station A, we have an angle of elevation of 41 degrees, and station B, there's an angle of elevation to the rocket of 75 degrees. And the question is asking, what is the altitude of the rocket? And this is important here. It says, note, both tracking stations are located to the left of the rocket. Okay, so we've got a rocket in the air. Let's kind of label that. Let's put this big dot here. There's our rocket. You got this rocket in the air. They say you have two stations. Now in this problem here, they don't tell us which rocket tracking station is which. We don't know where the 41 or 75 is, but we know it's to the left. So what I do know is that a larger angle means larger opposite side. So I know that this second station right here, the angle to that rocket would be less. So therefore, this must be my 41 degrees, and then this must be the angle of elevation, in this case station B of 75 degrees. So let's go ahead and draw that. Okay, so I actually found a GIF that we could use for a rocket. It's a little better than the dot that I had there. So if you take a look here, here's our diagram. The observation for this one here is if you take a look here, we actually have a non-right angle triangle right here. And I'm hoping I can use the sine law for this. Now, I know that the measure from here all the way around will be 180 degrees. Since that's 75 there, it must be the case that this angle B must be 105 degrees. If that adds up to 105 degrees, then I know that 105 and 41 add up to 146. I know that this triangle here has to add up to 180. So this must be 34 degrees. So I'm hoping I can use the sine law on this. What I want to do is if I can find this length here, let's label this with a y. If I can find this length right here, then I can use that, this length plus my angle 75 degrees here. Using my sine and cosine ratios, I can actually solve for length of x. So let's go ahead and do that here. In this case here, we're going to have, using the sine law here, we have y divided by the sine of 41 degrees. So again, I'm taking my y value divided by the sine of 41 degrees has to equal, well, the length of 20 divided by the sine of 34 degrees. Then we multiply across by the sine of 41. Compute this to 2 decimal places. We get 23.46. All right, I just cleaned this up a bit so we can focus on our right angle triangle now. Now I'm focusing my attention on this right angle triangle. You'll notice, and now we just got this value. We just discovered that the length of the hypotenuse of this right angle triangle is approximately 23.46. I want to solve for the value of x. So in this case here, directly opposite, This will be my opposite. This will be my hypotenuse. This will be a sine question. So this would be the sine of 75 degrees is going to be my opposite, which is x, divided by 23.46. And multiplying across here, my x value, which is the altitude of the rocket, is approximately 23.46 sine 75, which is equal to 22.66. So for this question here, the rocket is approximately 22.66 kilometers from the ground. All right, this concludes the lesson on the sine law. You'll notice here you can apply the sine law to word problems. And we also have, these are the two basic types you're going to get with the sine law. Either in a situation where you're given the lengths of two sides and an angle, or a situation where you're given two angles and a side length, in which case that's when you're going to go ahead and use the sine law. All right, thank you.